Hello, hello. Uh,
Hello,
uh,
Professor.
Hello, Yedaya. Thank you. I know where you live. No, you know where I live. Hello. That
Good
sounds
morning,
weird. Good
Professor.
morning. Oh, that's voice too. Good morning. I think that was, wait, I didn't see. That was, wait, hold on. I'm going to change the view. Oh, where's going on? Ah, yes. Oh, that was Lee. Oh, was that? Oh, good morning, Lear. Or was that
Thank
mom?
you. Good
Oh, good
morning. No, it was
morning.
me, Lear.
It was. Okay. Good morning. Good morning. Excellent. And good morning. Sorry, I didn't have the right screen on. Okay, so Lear, yes. Hello. Hello, Vicky. Hello, Bridget. Hello, Yadaya. Hello, Aminata. Hello, Sonam. Hello, Joel. Hello, David. Now I'm gonna do the chat. Hold on. We'll get uh, good afternoon, Vicky. Hello, Joel. Double double. Oh, and there's Aminata. For real, comma yo. Uh, Hello, good afternoon, Raina. Good afternoon, Caitlin. Good afternoon, Melanie. Hello, Bridget. Hello, Anthony. Hello, David. Good afternoon, Sonam. Good afternoon, Victoria. Good morning, Fabia. Oh, yeah, some debate on what time of day it is, but yes, I'm doing well. Thank you. How about you? No time to answer. Good afternoon, Roger. Good afternoon, Zoe. Good afternoon, Aminata. Oh, and Abid is coming in. Okay. Oh, and Kian is coming in. Okay. 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 Yeah. So we can like do physics, I think. Um, let's do some physics. Yes, hang on once. Yes, let's do some physics. Um, very la I'm just trying to be careful of that. Like the goal of today and the next day or two of this week, the goal is to get to um this second equation on the board right here. That's the goal. We have not said it yet. It is the goal. It will very much help you with lab 3, which okay, tell me very quickly in the chat, privately or not. I believe you're in lab 3 right now, correct? And I guess what I really want to know is, oh, and hello, Abid. Good to see you. Okay, sorry. Um,
Yes.
oh, you just finished lab 2. Thank you, Aminata, and thank you, Anthony. Oh, even better in a way. Oh, so you're not, oh, good, good, good. So you haven't started lab 3 yet. Okay. Um, Great. So then, because often things we discover things in the lab first and they're sort of confusing, and and then we like get homework on them and they're sort of confusing, and then finally they sort of get clarified in lecture. I mean, that is the way it is, good or bad. But actually, I'm sort of glad. So this means, in a way, I'm going to give you a jump. Everything I'm going to start saying today will help you when you move into lab 3. And even if you start doing the lab before I finish all these things that I'm going to say, uh, I will certainly have said them in time for you to write your report for Lab 3. Um, so I'm glad we haven't. So there's still plenty of time for all that. So good. So this will be helpful. Okay. So just when is homework 4 due? Oh, it does. Okay. Wait. Thank you. Let me look. There's a clarifying question about the homework sequence in the chat. And yes, I don't mean, and I realize things have gotten a little jumbled. So because Google Classroom says home. Okay, bear with me for a second because whatever the issue is, let me try to look at it and fix it right now. Hang on, because that is definitely important. Oh, yeah, and I remember because I tried actually to adjust. Oh, I know what you're talking about. I thought I had. Oh, I see. Yeah, 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 yeah. All right, all right, all right, all right. I'm gonna fix this right now, and I'll explain. Thank you, person in direct. And you should submit for points for this. Um, yes, the person in chat. I see what I did. All right, give me a second, and I'll. All right. Okay, bottom line, right? There was accidentally what I it looked. It was the case a minute ago, up until a minute ago, that homework 5 was assigned or due before homework 4, which does not make sense. Um, so thank you, direct chat person, for bringing that to my attention. So I've just changed homework 5 to make it later. Oh, so I should check again homework 6. Hold on. Oh yeah, no. So this works out. It works out. Yeah. So homework 4, to be clear, you have a little break now because I have to sort of catch up with you. Homework 4 is not due till March 12th. I mean, as it says in Google Classroom, I didn't change that. I just like leapfrogged the other thing uh, to later in the calendar. So the next homework is not due until like a week from this Wednesday. So that gives you time to catch up with stuff we're doing now and time for me to catch up and to explain the material that you would need to sort of understand in order to do homework 4. Like literally, if you try, especially if you haven't done lab 3 yet, and I haven't talked about this yet, if you try to do homework 4 right now, there you would be completely frustrating and confused for two reasons. One, we're not even up to the material yet, but two, homework 4 is very underwritten. Like it doesn't even sort of make sense. It assumes that I've already kind of discussed in class what homework 4 is about. Okay. So don't even try homework 4, please, until like I give you, or you can remind me every day in class that I need to give you some context for homework 4. There is no context for it yet. So whatever time we have right now until I say otherwise, just be catching up and revising old things and so forth. So thank you for clarifying that. And then homework 5, uh, is after that. And frankly, homework 5 is optional. I'll make that, I mean, it's all sort of optional, but it's even more optional than optional. I'll make that clear as we get closer. But okay, so thank you, direct type person. Also, someone's in the waiting room. Okay, right, right, exactly. Direct chat. Sorry, as a direct chat person is saying, he or she was reading it earlier and assumed we needed some type of equation or concepts that we didn't learn yet. Exactly right. So thank you for being so on top of it. So there's nothing you can do about homework for it yet. So just be catching up and trying to absorb this material. But every material, everything I try to teach you in the next couple of days, and I guess that includes Thursday of this week because I guess Thursday is Wednesday or something. Everything I try to teach you this week, very much also put in your bank for preparation for labs 3 and 4. Like those will be a lot easier to understand if you start following what I'm saying here in class. Okay, so there's more people coming. So, um, I will quickly go. So I'm going to screen share. So I'm going to switch. So, but first I'm going to continue a little bit with homework, going over homework 2. So we were in the middle, and I'm not going to solve every problem from homework 2 in class, but I'm going to get the main ones across that we need. So I'm going to do a quick screen share here. Right. I'm going to try to do something quickly. Okay. Oh, okay. Thank you, person who just told me that about leaving for 5 minutes. Cool. Thank you. Okay. Okay. So this is where we are now. Like what we just went over on last Wednesday, and it was F and G. We went over F and G here. And if you weren't here, you should definitely watch the videos. We went over them, but it took us a whole period to expand on the implications of F and G. The main implication is that we now, from here on in, when we talk about oscillators, we talk about them. Our discussion must always include this idea of a phase constant. from now on. And the phase constant is like the head start or the delay with regard to cycle. So you need to know that, and we'll get back to that. But then we just did H together last class. And in H, we were saying to ourselves, okay, now that we've realized that the cosine solution, the cosine way of describing a simple harmonic oscillator is not the only way. Like we thought harmonic oscillator was like cosine omega t. Then we realized in part F and G of this homework, we realized, oh, it's not necessarily cosine omega t, if by that we mean cosine omega t plus zero. It could be cosine omega t plus phi, where phi stands for this number of radians called the phase constant. Like we realized, oh, there's more than one solution to the differential equation for harmonic oscillation. So once we realized that, we were like, oh, should we backtrack all the way and realize like maybe we don't even, maybe cosine's not even the only way to go. Like, could we try sine, for example? By the way, it doesn't, maybe we do this in an exam, but it didn't even do this in homework. We might have backed right before H and said, how about sine of omega t? Like, could that work? And the answer is yes, it could. And especially once you allow for a phase constant, sine could get you the same information as cosine once you allow for a phase constant, because you all know in one part of your brain, cosine of any given angle is the same thing as the sine of that angle plus or minus like 90 degrees. If you know what I'm saying, like, right? Like once, or if you look at the graphs, once you shift a cosine graph by pi over 2 radians, what you have is a sine graph and vice versa. So once we're allowed to have a phase constant, that's one of many reasons that if you believe in cosine, you should believe in sine. And they both have that property, that important property, where the derivative of the function gets you back to the function with a constant and a negative sign, right? That's a mouthful, but that's what we're looking for here. When we're looking to describe harmonic oscillation, we're looking for a function for which it is the case that when you take two derivatives of it, you get back itself times a constant, and the constant could be 1, times a negative sign, right? That's really the mathematical implications of Hooke's law. So now that we realize, so cosine does that, sine does that. Cosine's more convenient because it like starts with a y-intercept that isn't 0, and that's what we want for a physics experiment. But cosine does that, sine does that. So now we're saying in part H, we're saying, well, wait, are there like totally other functions that do that? Like, could you describe a simple harmonic oscillator with E? Since when you take a derivative of E, you get back E. Like, whoa, that, I mean, that sounds like it's got like some potential there. The rate of change of the function is like related to the function itself. So last class, we did H, we tried E to the negative omega t, we took two derivatives of it. I'm just thinking whether I should switch the screens. I'm in a second, I'm going to switch the screens. We took two derivatives. I'm talking about H now. Like we already did it, so I'm not rewriting it. We took two derivatives of e to the negative t, and what we got back, I'm sorry. We took two derivatives of e to the negative omega t. And what we got back, if you're looking at your notes from last Wednesday, or if you're looking at the homework, that was due, when we took two derivatives of e to the negative omega t, what we got was omega squared times e to the negative omega t. And i.e., what we got back was omega squared times x. And that really looks darn close to what we want to get back. It looks like the original differential equation for simple harmonic oscillation. Like I'm looking at part I on the screen now. Like the question is x equals e to the negative t. Like when it says in I is x equal e to the negative omega t, a solution to d2x dt squared equals negative omega squared x. That's I mean, what it's saying in English is x equals e to the negative omega t a correct, reliable way of describing or predicting a simple harmonic oscillator. Like that's what that's asking, right? If it's a solution to that differential equation, it means does it describe what that equation describes, which is simple harmonic oscillation. And it almost does look like it is. Because when you take two derivatives, you get omega squared x, but it isn't because what you don't get is negative omega squared x. Like I'm making a huge deal about this and then I'm going to move on. I'm saying if you're following the class material, like our goal is to find a function where when you take two derivatives of it, you get back itself times a constant. And that constant we often now call omega squared. So that's all good. But then you also are supposed to get this negative sign. And if you don't get the negative sign, you have done something interesting. You have satisfied some kind of differential equation. Like for sure, you've discovered something that's important in nature, probably. But what you haven't done is describe a simple harmonic oscillator. If you get back, as we did in part H, if you get back positive omega squared x, that's not the same thing as negative omega squared x. And the negative sign, and so it's not a simple harmonic oscillator. We need the negative sign to mean oscillation because the negative sign is the negative sign from f equals negative kx. The negative sign means the thing, no matter where it is always coming back to the center. And that ultimately means that the velocities, whenever they're positive, they're eventually going to be negative again. And the accelerations, whenever they're negative, they're eventually going to be positive again, and so on and so on. So like all of the stuff from homework one, all of the derivative, like it means that everything is oscillating back and forth, all the derivatives to infinity, as long as we have that negative sign. And but if not, then not. Okay, so answer I was no, it is not a solution. It's not a harmonic oscillator because we didn't produce a negative sign. Now I'm going to move on to J, right? But I'll tell you this. You might think, well, that's because you stuck a negative sign in the exponent, yo. Like, why'd you do that, Yaverbaum? Like, maybe you should try without the negative in the exponent, then you'd be okay. Try it. I dare you. No, like, good point. If you were thinking that at all, darn good point. Like I stuck in that negative sign, sort of hoping it would produce a negative sign, but it totally didn't because it canceled itself out when I did the chain rule twice. So you really, if you're really being a scientist about it, or you're really following this whole thing, or you're getting bored of my voice, which I am, you might want to just try on a piece of paper. What if you just try e to the omega t? Try that. Try taking two derivatives of that. Smart. I'm not mocking. Smart. But if you do that, you'll see, you might even see already in your head. If you take two derivatives of e to the positive omega t, you're still not going to get a negative sign. Like two negatives make a positive and two positives make a negative. So either way, it's almost like we're kind of right. So so since the chain rule happens twice, since we're squaring whatever's in there, it doesn't seem like we can get a negative sign. The square of a negative is a positive, and the square of a positive is a positive. So it seems like there's ain't nothing we can do. Except, I'm going to switch the board. I'm going to switch the board and go on to J because when I put it like that, wait, we're trying to get a negative sign by squaring something. But when you multiply a positive by a positive, you get a positive. And when you multiply a negative by a negative, you still get a positive. So it seems like there's no way to take a number that if you multiply it by itself, you get a negative. When I say it that way, what comes to my mind are, wait, isn't that the whole point of freaking imaginary numbers or complex numbers? Like, I'm going to switch the board. But if you looked at part J and you were like, what? Is he all of a sudden talking about imaginary numbers? Yes, I am. If you're like, wait, did Yaverbaum just out of nowhere just throw in I is defined to be the square root of -1? Like, does he mean that like as in the imaginary number I? Yes, I do. And if you're like, Where did that come from in the middle of a physics class? Good question. Especially if you think physics is supposed to be about reality. And now suddenly I'm talking about imaginary numbers. Like, what the what? But no, the what is exactly what I just said. Like, we're trying to come up with some kind of number that if you multiply it by itself, you get that negative sign we need. And we already have, that's what I is. I mean, that's what imaginary numbers are. The numbers such that they're square roots. I mean, the numbers such that their squares are negative, right? So they are for a purpose that is in reality. It's kind of bad that they're called, I mean, they are imaginary as much as any numbers are imaginary, but no more than that. That's why, as many of you know, we really ultimately call them complex numbers. They certainly are complex. So wait, so I'm gonna switch the board. I'm gonna do, so that's why, oh, and if you're thinking, wait, I never took a class in complex numbers. No, yeah, it's fine. I mean, I did, but like you don't have to. What do you need to know about complex numbers in order to get this far in physics, what you need to know is exactly what it says on the sheet. You just need to know that I is defined to be the square root of -1. That's what I is. It's the number that produces the kind of result that we're looking for here. So I'm going to switch the screens. I'm going to switch the screens. Switch the screens. Don't cross the streams. Hold on, but how do I? Hold on. Sorry. Okay. What? Hello. Huh? Okay. Hold on. And I'm going to switch. 1 second, 1 second. Like you really need two of me in your life right now. You do not need two of me in your life. Hold on. Hello. Okay. So, right. Okay. So I'm not doing all the methods. I'm sort of am, but I'm not going to draw a whole diagram out. You are. I'm not. Sorry. I'm just getting the screen again. I'm sorry. There's stuff in the chat. 1 second. I'm sorry. Okay. That's fine. Oh, let you in again. Yes, I can let you in again. Sorry. I missed that. Oh, I really missed that. All right. Well, if someone's, yes, I can let you in again if relevant. And good afternoon, person who said good afternoon. All right, so now we're literally going to take a derivative of a complex function. That sounds intimidating or exciting, but you don't need to know any new knowledge. Like you know how to take derivatives, you know how to do, well, you need to know what we already said. You need to know that if y equals e to the x, then dy dx equals e to the x. Like you need to know that the exponential function is the function for which the derivative is the function itself, right? Derivative of e to the x is e to the x. You know this. We used it last. And you also need to know the chain rule, like last time. And you need to know that I is a funny kind of number, but it's just that, a number. It's a constant number. So all the rules of derivatives and all that apply to it the way they apply to constants in general. So therefore, the derivative of this, so I'm saying, well, so the derivative is I omega e to the I omega t. Right? I just did chain rule and I just treated I like it's a freaking number because I is a freaking number. Okay, so that's it. That's the answer to that one. So what? Well, the so what never comes until I do the second derivative. Yeah, hello, hello. Okay, so the second derivative, I just do the chain rule again. So I get, oh, and just like noting, so remember, x apparently equals e to the I omega t. So the second derivative do the chain rule again. So I'll get I squared omega squared e to the I omega t, right? Fine. But what is I squared? Well, by definition, I squared is -1 because the definition of I is the square root of -1. So I squared is -1 and I cubed is -1 times I, right? Negative I. And I to the fourth is I squared times I squared, i.e. -1 times -1, i.e. 1, right? I'm just saying. I mean, did you have to memorize all that? No. But does that all that make sense? As long as you know the definition of I, yes. So okay, so what I'm saying here is that equals -1 times omega squared. Hello. E to the I, hello, e to the I t, omega t, right? Which is to say that d2x dt squared equals negative omega squared e to the I t. That would be step 5, final answer circled. And that's kind of interesting, I think, because if you go to k, so K says, is X equals I omega T a solution to the differential equation that we're dealing with? And I say, yes, it is. And that could be, that is fascinating. In other words, I'm saying, can you use exponential functions to capture the same information as cosine functions or sine functions, even though cosines wiggle back and forth in the manner of oscillators and exponential functions just like monotonically go off up or they monotonically go off down, right? Like exponential functions are like woof or something like that. Whereas cosines and sines are like, right? And you have to do the sound effects, otherwise it's not, no, right? So it sort of it makes sense that we would use cosines and sines to describe oscillators. I would not have physically thought we could use exponentials to describe oscillators. I wouldn't, because exponentials just go off in a direction. But then I kind of might have sort of thought that I might have been able to because exponentials have that self-differentiating property to them. They have that feedback property that we're looking for. So I tried an exponential, but like it didn't work. And like, okay, so I'm not really surprised because like I kind of didn't really think I mean, I kind of thought it should work, but it kind of would have been weird if it did work. But then I tweaked the exponential and threw in a complex number, like literally, and then it worked. So what we're saying is exponential functions can behave like cosinusoidal functions as long as the exponential function is a complex exponential function. Like what? Yeah, this is why it starts to actually become worth like taking math classes and thinking about math. And like math gets super interesting in its own right at a certain point. Once like you just like you have to learn the alphabet before you can like learn poems or read literature. We take a long time like slogging through the alphabet of math in a way, thinking that's all there is to it, but that is not all there. That is just the alphabet of math. Like I'm saying, and I'm going to move on, but I'm saying it's actually a really, really deep and important mathematical result that if you put complex numbers together with exponentials, you get cosines, or vice versa. You put complex together with cosines, you get exponentials. They're all tied together in the end. And that's not just an abstract math point. In the end of the day, imaginary numbers are not imaginary. We use them in connection with exponentials in order to describe oscillators. It often turns out to be, and for example, in PChem, it will be much more useful and convenient to describe oscillators. I'm just summarizing. What I'm saying is this. So particularly when you get to PChem, or those of you who are in any way going on in electrical engineering or like anything like that, yeah, electrical engineering, circuits, everything I'm saying, and I'm going to continue to say in this course about how to use cosine to describe harmonic oscillators is all true and relevant to this course. But it turns out it's actually a lot more useful in a lot of contexts, including PChem, to rather than using cosines, to use complex exponentials to get to the same results, but actually with more straightforward mathematics, um, and more economical management of information. So just to know, for those of you who might at all be going on, as I say, in PChem or in particularly in electrical systems, just know this. Just so you know, exponentials and cosinusoidals and complex numbers are all like tied together ultimately in this thing known as Euler's equivalent, Euler, the great mathematician. Um, any one, they're all related together, and why? I'll just say this quickly and I'll move on. Or wait, does it? Wait, I'm just yeah, yeah. I'm not going to do that right now. Just to move on. I mean, just before I move on, think about it. Well, yeah, I'm just going to write because it may be on the exam. I'll just write it. Oh, whoa, I did not mean to do. Sorry, hold on. It's paging Dr. Freud. Okay, hold on. Okay. Just know, and we're gonna move on, but this is like a math physics connection. Again, what I'm saying is in this class, okay, I don't want to confuse anybody. I don't want to confuse anybody. In this class, we're gonna go on with the cosine solution, so to speak. We're going to keep using cosine to describe simple harmonic oscillators. And from these cosines and oscillators, we're going to build waves. from these cosine. But it's but cosines with a phase constant. Like what we learned last class is that just a simple cosine is not good enough, not general enough to describe oscillation and ultimately propagation. We need cosine with a phase constant. So then I'm saying, yeah, if you really want to be general, you need a phase constant. If you really want to cover you need a phase constant, but then that makes you realize you could just as easily be using sine to express the same thing, or some combination of sines and cosines, or you could use exponentials as long as they're complex exponentials. It turns out that complex exponentials can capture and convey the same information as sines and cosines. Well, it turns out that exponentials can, as long as they're complex exponentials. Complex exponentials wiggle the same way that cosines and sines do. And they do so according to this mathematical discovery known as Euler's equivalence. Now, I'm not saying you have to memorize that, although, again, I think for many of you, it will come up later in your life. I'm not saying you have to memorize that. I'm not even saying that you'll ever have to do much with it in this class. But I am saying you should understand that it's not a surprise, that it actually makes some level of sense. What I want you to understand is that whatever we're talking about here with these differential equations and with these cosinusoidal or exponential solutions, we're talking about functions that generate their own rates of change, right? We're talking about functions that when you look at their rate of change, bring you back to the function itself. Feedback. Like the whole original thing of this was a mass on a spring. We're trying to predict where is the mass going to be when. And we say, I want to know what X is for any given T. And then someone says, well, it's physics. So in order to know what X is, you're going to have to know what acceleration A is. And we say, okay, in other words, d2x dt. Like in order to know position ever in physics, you need to know the second derivative of position. But then we say, uh-oh, with an oscillator with a mass on a spring, the second derivative of position is determined by position itself. That's the hook. No pun intended, pun totally intended, to this whole thing. It's the part that never happened in physics before. We're saying the second derivative of position with respect to time is determined by position itself. d2x dt squared equals negative x. That, right? That's feedback. The output is generating further input. That is the key to this whole phenomenon. It creates a differential equation that needs to be solved. Now, I want you to note and makes math interesting or challenging or both. I want you to notice that it's not a surprise that what sines and cosines describe also can be described by exponentials and complexes when you put them together, because look at the pattern. If you take, right, sine, you take four derivatives of it, you get back to sine itself. Exponentials, you take four derivatives of them, you get back to exponentials themselves. I'm not saying you have to take four, but you could take four, right? If you, right? So if you take four exponentials, you definitely get back to itself. Four derivatives of an exponential. If you take four derivatives of a sine, or a cosine, you definitely get back to itself. And if you raise I to the power of 4, i.e., if I is stuck in as some constant in one of these functions and you do chain rule to it, if you raise I to the 4th power, you get back to itself. Or if you cycle through, you see what I'm saying? So there's something deep going. All of these functions have this cyclical feedback nature that is the essence of simple harmonic oscillation. We're trying to get to the essence of it. We capture that mathematically. Here's mathematics that is perfect for that description. So that's the point of that. So I'm going to leave that now. I mean, there's more to homework too. I understand. Like there's like some, well, maybe I can, there's more. I mean, there's like a little more practice with cosines. And then there's like this dot product, cross product thing, which we definitely need. But I think I don't want to get into today. Um, Yeah, I'm not going to get into today. You can remind, and I think we've talked about the dot product in connection with work. In fact, we definitely have done the dot product with connection with work. We have to contrast with something called the cross product. I'm not going to go down that. So remind me before I go too far astray. I don't want to do that now. I want to walk away from homework two for now to start preparing you for lab three and so forth. I'm just going to look at the screen for 1 second to see if there's anything. Yeah, I'll say this. All right, it's 1 o'clock. Yeah, okay. I'm going to quickly do the cosine. I'm going to just write down the answers right now. I'm screen sharing again. I mean, I'm going to switch the screen again. Hold on, just so you, because everything I just said now wraps up. I just wrapped up like all of this part one of homework two, so that we could just stay linear and stay as a class. What I'll do very quickly now is write down the answers to this part. This is meant to be practice of cosines, which I think you've gotten plenty of, but also it's trying to drive home. If nothing else, I'll just say it's trying to drive home the how a phase constant works mathematically, and hopefully you can link that in your mind to how it works physically. Um, yeah, that's what it's trying to do. So I mean, oh yeah, okay. I'm going to say this in English. Like, look at your screen right now. It asks you a bunch of questions about x equals 4 cosine pi t. Well, uh, yeah, no, I'm not gonna. I'll just give you the answers to this. I mean, but it's trying to have you see what effect it has on the graphs or on the values when you add in a phase constant. And the ultimate point, right? When you add in a phase constant, it just means that the value of the function at t equals 0 shifts by that amount. But here we also change the omega. So it's not a very clean comparison. It's sort of having you practice two ideas at once. And by practicing both ideas at once, it may not be a very clean recognition of either of the ideas. So I'm just going to write down the answers. And if you have any question about the answers, definitely stop me. Like this would be the time because then I'm going to move on. So bear with me for a second. I'm going to write down the answers. If you have any questions, do tell me and I will discuss. But other than that, we're going to move on. Why is it? Sorry. Okay. And do check me because I'm going to do these off the top of my head right now. So it's actually, so you should check that these answers that you like, these answers that you're comfortable with them, that you got them in your homework. I'm not doing all the steps. I'm just doing answers, but I'm doing it off the top of my head. So you should also check because I might make a mistake. This would be a good opportunity for you to check me. Okay. All right, well, and obviously, if you get any of these wrong and you see, then you should redo, for more points, resubmit, whatever. Um, Okay, no, I'm not gonna write. I'm just gonna write the answer. Sorry. Okay, so given that at t equals 0, what's the value of x? Well, cosine of 0 is 1, so x equals 4. Okay, you should literally, honestly, you should, I'm looking at the chat in 1 second. You should really check that your answers agree with mine, either to make sure you're okay with this or to make sure I just didn't make a mistake because I just did those in my head. That's A, and but I'm gonna look in the chat. Hold on, and I'm gonna do B, and then I'm gonna move on. If there's oh. Okay, so I don't see anything in the chat, so I'm gonna assume I'm okay so far. And again, this is an opportunity for if you didn't get a perfect score in the homework to like redo things for more points of it. So now Ay, okay, so B, I don't know why the Roman numerals do what they do, but they do. Oh, sorry. Uh, no. No. Sorry. You should definitely check me on this last one, and I'll tell you why. But I think that because I don't want a negative answer for time. Like you could get other answers, but I'm really losing my moment. Sorry. Yeah. I don't want. I mean, it's not like time. It's not like it's never meaningful for time to be negative, but here it would mean before the experiment begins. So that's like weird. So I'm looking for the smallest possible value of time that's actually positive. So and again, if you're with me so far, so in 8, I'm looking to make like I know the cosine of 0 is 1, but I don't see a way to make the cosine of 0. I don't see a way to make the inner parentheses 0 without making time negative. So I'm making it the smallest value it could possibly be while time is still positive. And in my mind, that value would be 4 pi. Like 2 0 is too small, 2 pi is too small, 4 pi is the smallest right? I'm just talking out loud, but you should stop me if you don't know what I'm doing in eight. And you might have gotten a different answer, but check if your answer is negative. I'm looking for the smallest possible positive answer I can find, even though the question didn't specifically say that, but I think that makes sense physics wise. And then, uh, or did I just, yeah, and same, I'm going to do the same thing for nine. I don't want to get this all crowded. Oh, but for nine, zero would work. Yeah. Okay. So nine time equals zero. So those are my answer. I'm going to look it back in the chat. Sorry. Oh. Right. Oh, good. Oh, thank you. Okay. Thank you, direct chat person. Looks good. I'm glad. You got negative one fourth. So, right. I'm in effect shifting one period, except I think you shift one period. Yeah, you very good. So you should shift one period, which would mean two pi. Someone in the chat got negative one fourth for their answer to eight, which I do agree with. Right. But I'm just trying to avoid that. So, so that's right. I'm looking for the time that's one period ahead of that, which is to say, eight fourths of a pi ahead of that, right? Like I'm thinking in fourths here because the argument of the cosine is in fourths. So, right, a period is two pi. I'm talking to everybody, but I'm like, I'm really glad there's somebody in the chat is like with me. Um, if you got and I'm assuming they're also speaking for a lot of people. So if you got negative one fourth as your answer, I'm not saying that's wrong, but I'm saying as a physicist, if you think about it, that means a fourth of a second before the experiment began, which you would have a hard time like accessing that. So and literally that's what it means, right? I mean, anyway, it literally means one fourth of a second before you started your stopwatch. So it's not meaningless, it's just hard physically to access. So yes, I'm saying we better look for an answer that has all those properties, but a period later, what would a period later be? It would be 2 pi later. Well, if I'm thinking in terms of quarters, of fourths, since that's what's happening here mathematically, I would think of that as 8 pi over 4 is the same thing as 2 pi, 8 fourths pi. So one of those fourths brings you to zero, and the next seven brings you to my answer, 7 fourths. Right? So hence, so I'm agreeing with the person in the chat. I'm thanking the person in the chat. They should submit for points. And also, to be totally honest, I'm also further demonstrating why I think my answer actually makes sense, even though it may look like it came out of nowhere. 7 fourths into the experiment is where X would be back at amplitude position. Okay, that's that. If no, now, so we're going to call that a wrap on homework two for now. There's also the cross product dot product business. I will get back to that soon. Just remind me before we get too deep into like maybe before we get into homework five, remind me because we'll need that for later, but we don't need it for now. So now I'm going to, so we have 18 minutes. Just hold on, thinking for a second. You haven't started lab three. You know what? You know what's even better would be even more organized, I think, for all of you, or I think more satisfying for many of you. Okay. No, you know what? I'll just do it. Sorry, I'm apparently I'm feeling, hold on. No, okay. You know what? I apologize twice. Let's just finish this homework so we can put it to bed. Uh, and then, then we can quickly do homework 3 and put that to bed and we can, so I'm going to finish this. And again, if this, any of what I say helps you now redo the homework or still submit it for points, you're welcome to do that. But, so I'm switching screens again. I apologize. Or maybe I am in the screen. Yeah, I'm switching screens again. Okay, so we're here. I'm just gonna do that. I just the reason I almost didn't do this now is because this total left turn. It doesn't seem to have to do with anything with what we're doing, and in a way, it doesn't. But first of all, it does bring us back to the whole concept of work. Remember, work is the path integral of force, and work transfers energy. But work is the path integral of force, and path integral means it's the integral of the dot product of force vector with respect to displacement vector. So work is a dot product. And we did discuss that a couple of weeks ago, like in the context of conserving energy in a mass spring, i.e., oscillating system. But the other thing that this is other math that we just need for later in the course. To be honest, what we really need is when we get to magnetism. So don't look too hard for connections between part 2 and part 3 of this homework. But I'm just going to bang through this now so that we have all the math tools we need for the rest of the course, which is the idea of the homework. So, and everything you need to do, everything that you need to know to do what I'm about to do or to have done this homework is written right there, right? What it says is that the dot product between two vectors, produces a scalar whose value is the length of one vector times the length of the other vector times the cosine of the angle between them, right? Like now this, I mean, stop me, but I believe we've discussed this. The whole idea here is that the dot product or scalar product of two vectors measures the extent to which the two vectors are aligned with each other, measures parallelism between the two vectors. Like the bigger the dot product is, all other things being equal, the more parallel the two vectors are. And that's why it produces a scalar, because it's really asking how much could we treat these two vectors as though they were just two numbers on a number line. And that's what we do when we perform work on a system, on an object, right? We push it through a space and we're asking like how much of our push is aligned to the path, the space along which we're pushing it. Whatever that product is we call work, and it will transfer a lump of energy to that object, a lump of energy, not energy east or energy west or anything. It'll just give it an amount of energy, a scalar amount, right? So the dot product between two vectors measures how parallel they are and produces a non-vector quantity as a result, produces a number, right? That's the dot product. I'm just summarizing this quickly. Now, the cross product is the contrast to that. The cross product is a product of two vectors that produces a vector. It actually produces an answer that has direction in it. And that final answer is an indication of how much of a role direction was playing in the relation between the two original vectors. The cross product measures how directionally not aligned two vectors are. It measures how perpendicular they are. It measures how much direction is making a difference in their relationship, how much we cannot treat them as two numbers on a number line. So the cross product produces something that isn't just a number on a number line. It produces a vector, a quantity with magnitude and direction. So what this is saying on the sheet, and I'll start doing the answers like right now, what this is saying on the sheet is that the literal, so look up in the top right, like on the sheet, I mean, on the screen share right here. And I know I'm just talking, what else is new? But if you look to the top right, notice a subtle distinction between what's happening here. What it's saying in the top right is literally the dot product between two vectors is AB cosine, hello, sorry, is AB cosine theta, not, I mean, it's just saying the dot product produces a number, which is the number AB cosine theta. End of story. But when with the cross product, it has these double lines around the cross product. Like, what's going on with that? That's not a typo. It's saying that the cross product produces a vector whose magnitude, those double absolute value symbols mean magnitude. Because if you ever think about it, like what absolute value actually means in the first place is distance from zero on a number line, right? Like that's literally what absolute value means. So like the absolute value of -7 is 7 means the number -7 is like 7 units away, like the distance of it from zero is like 7 units, right? So double absolute value symbols, lines, means magnitude of a vector because it's like picturing it's just allowing for that, it's extending that same concept to more than one dimension, absolute magnitude of a vector is how far does that vector bring us from the origin, from zero, in whatever direction, in the plane or in a cube or whatever. Okay, so the double absolute value symbols mean magnitude of the vector. So what that notation is saying up at the top right is it's saying the cross product produces a vector whose magnitude is AB sine theta, i.e., the bigger the angle between the two vectors, the closer that angle is to 90 degrees, the more the two vectors differ and are, approaching perpendicularity from each other, the bigger the magnitude of the cross product will be. The magnitude of the cross product between the vector product of two vectors will be AB sine theta. What it doesn't tell you is what will the direction of that answer be. It doesn't tell you that yet. I have to get to that. But I just want you to know that is, a different type. That is a partial piece of information it's giving you there. It is telling you what the magnitude of the cross product will be. It's not telling you the entire cross product because the entire cross product would include direction as well. For what it's worth. All right. So now, having said that, I'm just going to again sort of bang through answers here because you need this whole concept. You need these two different forms of multiplication to do like physics. Hence, it's an early homework in this class. But now I think just to do this, that's all you need to know. So I'm just going to do it. I'm going to switch screens. And that if we do nothing else today, at least we will have just put like two big homeworks to bed and we can move on. And then homework 3, I'm sure many of you have noticed homework 3 would not take long to discuss at all compared to all this. So, sorry. So, hello, hello, hello. Okay. Well, uh, okay. Well, that's the answer to that. And you could check me again like you did before. I will explain this in a second, but let me just like write the answers out before. Um, for one and two, it's asking you to rank, the products from greatest to smallest. And the bottom line is dot products are measuring parallelism. Cross products are measuring perpendicularity. So dot products are greater when the angle looks closer to zero or 180, if you like. Um, and cross products are greater when the angle is closer to 90. And they're smaller when the angle is closer to zero or 180. So I just rank the angles that way. If you have any, I'm not trying to be weird, but okay. So if you have any questions, please ask. But if not, I'm going to keep going. I'm sure some of you would want me to keep going more than I have been. So that's it. Okay. So then three, assuming all the vectors have magnitude three, find the following. The result of this vector indicate the direction. Oh, okay. So this is what we're going to pause. Okay. So A. Sorry. Okay. Now I will hold on. I'm putting a question mark, not because I'm not sure, but to make a point. Okay. Uh, we have 4 minutes. Is this enough time for me okay, I'm gonna, yeah, okay. Well, first, let me look in the chat if there's any. Those are my answers, and you should really check if those are your answers as well. But the key, with 4 minutes left, I'm going to drop something slightly large on you right here. But just as long as we're doing this, um, like the reason I put question marks on answer D and E is because those are in. Wait, first of all, we have 4 minutes left. Raise your hand electronically if you're still with me right now. If you know where I am in the material, like if you're following where I am right now. That's one, that's two, that's okay. Cool. Thank you very much. All right, that's at least 12. Awesome. Okay, great. Because I'm going to say something now that is kind of big. I mean, and we'll have to talk about it more, but and it'll be where we end. Okay, so I shifted gears. Like what we're trying to do is just sort of blast through the homework so we catch up with ourselves. Okay, and hopefully, if you just raised your hand and there was at least 13 of you, hopefully you agree with my answers of A, B, and C, and F and G, or you see why you did wrong, or you see what you're going to do later, whatever. But D and E, you see, I agree with my answers, but they're not complete answers. You see, D and E ask you for cross products. So what I've just written there is the length. So the answers to D and what I'm trying to say is this. When you, and you can put your hand down. Thanks. Okay, I have 2 minutes. When you cross two vectors, you get a vector. Let's call that vector C, vector C, okay? The magnitude of that vector is AB sine theta. Fine. The question is, what's the direction of that vector? Like, I need direction to put on those two answers that I just, like the 9 and the 0, whatever. Like, those are just lengths. Those don't tell me in what direction. So, what is the direction of the answer to any cross product? I've never said before. Now, I'm going to say right now, when I say it, you've heard of it, but you might not have ever known that it came from this context. The answer, the direction Well, no, I'll put on the next page. It's two. Sorry. And I know I only have 2 minutes. The direction to the answer to any cross product is given or determined by something called, something you heard of in 8th grade, but never knew where it was coming from or why, the right hand rule. And the right hand, I'll just say it now because I know class is about to end, but then we'll develop this more later. The right hand rule says if you have two vectors, A and B, if you have two vectors, A and B, you take your right hand, you put your fingers of your right hand along vector A. Say vector A is going like that and vector B is going like that, whatever. And you put your fingers along vector A and you curl your fingers toward vector B. And wherever your thumb points, that's the answer. And meaning your thumb is always going to point in a funny direction that is perpendicular to the plane that the two original vectors were in. It's 130. What I am saying is that cross product produces a vector always that is it measures perpendicularity. So it always produces a vector that is perpendicular to both of the original vectors. The only way it can do that is to be perpendicular to the plane in which both the directors were formed or were found. So you put your fingers along one, you curl toward the other, your thumb will pop out of or into that plane, and that's the answer of the cross. That's the direction of the answer to the cross product. Weird, but true. But that's class. So that's the answer to those two answers. But we'll get okay. So they're both out of the piece of paper, in other words, or into the piece of paper. Okay. Okay, so let's pick up on that. So someone's saying in the chat, I want to hear about, well, actually, you can hang out for a second if you wait, I think, yeah, hang out for a second, person in the direct chat. But other than that, like, I will see you guys in 2 days and we'll pick up right from there. Thank you very much. I'm going to stop the